Our group is doing big data for our final project. I'm going to be talking about the history of big data. So what is big data? IBM says that big data is generated by everything around us at all times, and that every digital process and social media exchange produces it. Let's take a look at how this big data came about. Big data is a term coined in 1880 when it was found that the U.S. Census took 8 whole years to tabulate. So in 1881, punch cards and the Hollerith tabulating machine were invented to tame the big data and allow the job to be finished within a year. The next big event for big data was in 1944 when a librarian at Wesleyan University figured out that the library would have 200 million volumes of books by the year 2040, which would take 6,000 miles of shelves. This estimation really got the ball rolling on fixing the problem of what to do with all of this data. In 1948, a man named Claude Shannon came up with a theory for finding the minimal data framework needed to transmit information over imperfect channels. This is how we bridge the gap from thinking about new ways to store data to actually finding ways to transmit it. In 1966, centralized computers became available for use, and many organizations began to utilize centralized computing systems that enabled them to automate inventory systems. This helped eliminate some of the stress that came along with big data in the 1960s. In 1970, Edward Codd brought the idea of databases into common-day life by writing a paper about how information can be stored and accessed within databases. This technology is largely what keeps big data manageable today. In 1997, NASA researchers Michael Cox and David Ellsworth wrote an article about big data and discussed the amount of data that was being amassed was an issue for current computer systems. This brought much attention to the problem of big data. And in 2001, analyst Doug Lancey published a research paper outlining the 3 V's of big data: volume, velocity, and variety, which educated common folk as to what to look for in big data as it was becoming more of a common issue rather than just for big organizations. As for the future, big data continues to become a major issue as more and more people are collecting data and don't know what to do with it. Luckily, people are becoming more educated about the problems that lie within and can start being proactive about their data usage. Even last month, Wired.com mentioned in an article that big data is helping to improve efficiency in things like jet engines, where they can decrease in size because of sensors that generate large amounts of data regarding the engine's performance.
So our topic for today are the technologies of big data and how applications have so technologies. Big data requires technologies to efficiently process the large quantities of data with a time frame. The biggest technologies that companies use in big data include A/B testing, crowdsourcing, and data fusion. And of course, there's plenty of others, but I want to focus on these 3 for today. A/B testing, also known as bucket tests and split testing, is a randomized experiment with 2 variants, A and B, which are control and treatment in an experiment. It's a very technical form of hypothesis testing, and a way a company uses this technology includes web design. So this testing allows it to identify changes to web pages that increase or maximize an outcome of interest for something like, let's say, a banner advertisement. So this is a very useful tool for collecting data, and in fact, Google uses a version of this testing. Crowdsourcing. Large groups are required. It's a process of obtaining services, ideas, or content by soliciting contribution from a large group of people, such as an online community. So the idea of crowdsourcing is to take work and outsource it to a crowd of workers. This is a very useful tool, and a famous example includes Wikipedia. Wikipedia is well known, and it utilizes crowdsourcing. So a way they do that is, as you know, Wikipedia, instead of hiring writers and editors for their pages, they give they give the people the ability to create the information on their own, and this resulted in one of the greatest encyclopedias around. Next, we have data fusion. So data fusion is essentially data integration. Data fusion is an integration process of multiple data and knowledge representing the same real-world object into an accurate and useful representation. In simple terms, it's the means of combining and correlating data about a subject from different sources. Data fusion processes are categorized as low, intermediate, or high. So basically what this means is these categorizations represent a processing stage at which a fusion takes place. And so an example of this is data fusion might be combining data weather information in a city with daily car accident reports for that same city to see how bad the roads perform during a winter storm. Okay, so applications. So big data has allowed an increase in demand of information management specialists that companies such as IBM, Oracle, Microsoft, HP, and Dell have spent billions on data management software firms. In fact, in 2010, the industry was worth more than $100 billion, and it's continuing to grow at 10% a year. So, to give you an idea of how it affects real-world situations, big data analysts has played a large role in Barack Obama's success in the 2012 re-election. So, using information gathered based on voter opinions and demographic data, software applications could predict the shows future voters may watch, which led to efficient ad buy-ins for that specific channel. Also, Amazon.com uses big data applications. So, using big data applications, they can offer you recommended products based on the things you click. So, for example, say you were looking for a new pair of shoes and you browse around for some Nikes or some Reeboks. Amazon will use and collect that data and place ads around their website, leading you to other, sportswear that you may like. So that's one big thing, how companies use applications.
Now, let us delve deeper and examine how exactly big data is obtained. First, let us go over an overview of the collection of big data. The big picture poses three main questions. Who collects big data? How is it obtained? And what type of data is being obtained? So, who collects big data? It's a time-tested theory that we are always being watched. Here's a little graphic on the right that represents the current technological state of Big Brother, or the all-seeing eye, that now has the ability to track, store, and view metadata that's being obtained by many sources completely unknown to us as users on all of our technological devices. These include not only our cellular devices, the internet, and just generally going about our technological lives. First off, internet-based navigation sites like Google, Yahoo, and Bing are always using the information from our internet searches to bring us better results right to our fingertips. They includes, but is not limited to, having our cookies on our computers active and our user metadata understanding our likes, dislikes, preferences, locations, and personal info like occupations, interests, and current residence. Secondly, social networking sites like Facebook, Twitter, Google Plus and Yelp are responsible for doing exactly the same thing, but under the cover of us being able to interact with our friends through the convenience of our many devices. Thirdly, transaction data companies like Amazon and credit card companies like Discover and Visa, and including life insurance companies, all have transactional data, which includes information of things you buy and the frequency of your transactions. Third-party marketing providers like KBM, Axiom, and Equifax are the most unknown category of the bunch because they are contracted to gain access to user data, which aids in on-setting advertisements and marketing products to select target audiences. Recent exposure has brought upon much light to government tracking, which the onslaught of data that has been acquired by the NSA. The legality of the surveillance is under scrutiny currently, and our constitutional rights have been questioned over consistent debate over the past couple months. Moving on, let us discuss how big data is obtained. Credit card information, personal emails, social media, and online permissions all grant user metadata to big data sourcing companies that seeks personal information for one reason or another. Extraction of large-scale data is one option where information in the form of alphanumeric text and still image data is acquired. Massively parallel software is another method where software running on thousands of servers stores statistics, visualizing packages, and handle large-scale big data. Lastly, in-house solutions custom tailored to companies' needs and wants can also be outsourced, much like what Facebook do under its privacy clauses, and attain data in that way. Finally, let us talk about what type of data is being obtained. Methods including A/B testing, crowdsourcing, data fusion and integration, genetic algorithms, natural language and signal processing, simulation, time series analysis, and visualization return active and passive user data, which features data stored on one's own computer from commonplace activity that everyone engages in. This is just going about your regular day using websites and doing online searches. Our phones are also a huge source of big data acquisition. Whether we use an Apple, Windows, or Android device, our mobile carriers attain massive quantities of big data every year. Lastly, GPS traffic analytics are updated frequently on user-based applications like Waze and standard applications like Google Maps and MapQuest. These are all different methods in which big data is acquired and who is doing the acquiring.
Hi, my name is Robert, and today we're going to be talking about some of the uses for big data. Big data has been being used more and more every day in improving some of the things we use online. First thing that has been changed so much by big data is advertising. Advertising used to be a shot in the dark. It used to take a look at your demographic and say, you're an 18 through 24-year-old male, chances are you're going to like this. Big data does not go by these principles at all. Big data takes information from you. Say you liked this on Facebook. You've watched this video on YouTube, and it says on Yelp that you liked this restaurant. Now it'll combine some of these factors and all these things that you've done online into one little package that says, okay, these are the ads that we're going to give you. And chances are, now if you go on Google, you're going to see things that you actually might have either been to before or things that you do like. And that's because of this targeted advertising. Next, what we have is location-based advertising. Very similar to targeted advertising, except for the fact that this is using your GPS technology in your phone, and rather than targeting your interests or your likes, it's going to target where you are or where you've been. And then it's going to give you insight as according to you live here, you should go here, maybe this location, this restaurant, and it even combines in some cases with your targeted ads in order to make a judgment on you might like this restaurant in your area, just to give you something in your area that you would like. Next, we have recommendations using big data. It's very similar to the targeted advertising, with the principles that it's taking what you like and giving it to you online, rather than just using a demographic of things that people like you would like. It's more about you, not about a demographic. Now, this is used in many popular services today, including Amazon, Netflix, Hulu, Pandora Radio, and many more. And it just runs off the idea of big data, taking many data points of what you like and combining them into giving you things that you would like. And it's different from advertising, because instead of trying to sell you something, it's just going after making your user experience better and more enjoyable. Now, Amazon does this today through seeing products that you've already purchased, seeing things that you've liked to purchase or want to purchase, and also taking all the ratings of yourself, and then even other users that have bought similar products. And it combines these all together into making recommendations of things that you should buy in the future, and they end up usually being, at least in my case, things that I would actually want to buy, which is great. And Netflix does a very similar thing to this, which is it takes all of the genres that you're interested in, all the movies you previously watched, and it even accounts for things like movies you didn't like, and it will throw out those things you didn't like, and then put in the products, the movies that you did like, and it'll combine these all into giving you movies that you might want to watch in the future, or even more genres that you might like. Like if I was to go on Netflix right now, it'll say things by this director, the visually striking movies, Academy Award winners, and those are the movies I usually kind of watch, and it goes through that. And it really makes for a better user experience when using Netflix. Next, the weather and big data. With big data today, it's really changed the way that weather forecasting has worked over the last few years. It's been a big change from small amount of sensors and analyzing bigger amounts of sensors. Now we have all across the United States weather sensors, just because of the fact that it's trying to compensate for the amount of devices we have today and give you the most accurate readings for weather. And then the more and more information that is taken from the weather, it allows meteorologists to create a more diversified field in which the weather is given to you both accurately and more efficiently than before. Utilizing just the multitudes of information and data that are out there on the weather, you can start to see patterns in the data. And this creates scenarios in which you could see weather that has already happened and then identify when this weather is going to happen again in the future with these patterns. Lastly, big data has revolutionized the way that we can look at medicine today. This is just because of the fact that there are so many more data points when you analyze all this big data together. And this allows for more varied experiments. In one case, one experiment has to do with the supercomputer Watson, which was created by IBM. You may have heard about Watson before. This was the supercomputer that was able to beat Ken Jennings, the World Jeopardy champion, at the game Jeopardy. The way he did this was by utilizing a natural language translator, which was able to interpret what Alex Trebek, or what any person at that matter, is saying, and gauge what he's saying in a manner by taking all of the information that he knows in his systems, which in this case was thousands and thousands, leading up to actually millions of pages of text information, and scanning it for what the person, or what Alex Trebek in this case, is saying. And then by this, he's able to give the correct answer to a problem. Now, using these same exact principles of taking from natural language and then applying his information, he's able to work in the medical field. He actually has over 2 million pages of text stored in his systems now, and also 25,000 scenarios of medical cases that have previously happened, which has led him to be able to more accurately and more unbiasedly give a diagnosis on a patient than a doctor would be able to, because he doesn't have to deal with the fact of human overconfidence, and also he has just more information than a doctor would be able to learn. And as you can see, this has revolutionized it so much that I've started referring to Watson as he on accident in what I have recorded so far. So that should be a big indicator there of how far advanced this is. And lastly, here are my sources, and just in conclusion, big data has really changed the way we look at everything online today, and as the internet continues to grow, big data is going to continue to grow as well, and I can't imagine where it's going to go in the future.
When talking about big data, one must take into consideration storage and access. Most of the money that's being used in big data today is paying for storage. Storage needs to be able to handle petabytes and terabytes of data, which are large amounts. Storage devices also have to be scalable, so that an increase in data size is accommodated for. This is achieved through network-attached storage devices. Martin Glassborough, author of Clustered NAS versus Traditional NAS Solutions, does a great job at detailing the different types of network-attached storage devices in his article. In the past, traditional NAS systems were used more heavily. These were single storage units. Unfortunately, these units had to be connected to each device that was trying to access that information that was stored, as well as attempting to save to it. Scalability was limited by the amount of CPU and memory that a device and disk had, the disk space that the device had, and the ability for that NAS device to make use of the resources available. Nowadays, clustered NAS systems are being used, and they've been very effective and efficient in regards to big data. Clustered NAS allows for horizontal scaling across a number of devices, with all of them being active and able to see all files in the cluster. This is essentially a distributed file system. This is ideal for big data because it means that everyone within this cluster has access to the data at all times. It allows for one to add a device and increase processing power without having to worry about transmitting data that's on it to every individual device. Once a new device is added, once storage is used on that device, anyone can access it. Anyone can continue to store information to that same device as well. Everything is interconnected. If failure ever occurs, the load of the failed unit can be spread across the whole cluster, and information wouldn't be lost. If more storage is needed, all one would have to do is add a new disk that all the devices could see, and would have to purchase just one device rather than a device for each individual computer attempting to store and access the information on the device. As one can see, clustered NAS is more effective and efficient in regards to big data because it allows for a wide range of individuals to stay connected to the information, to all store and access the information simultaneously if need be, and it allows for scalability and accommodations for data sizes, data issues, and pretty much just allowing for big data to flow undisruptively. When talking about NASs in regards to big data, these systems of storage need to be able to be scalable. Dan Woods, author of 10 Properties of the Perfect Big Data Storage Architecture, pretty much explains what these needs of scalability are. Scalability is achieved by using a predictive model of capacity that's based on expected growth of data and applications used within the big data system. This includes the speed of storage and retrieval, as well as the number of staff that are employed in order to deal and handle the system itself. How is scalability compensated for? Well, the answer to that question is simply buy more disk, but that can be very expensive. And therefore, hardware needs to be created that is able to handle the size of the data used within big data, as well as be able to accommodate for the increase in data size, the increase in applications or the change of applications that are being used, as well as remain and preserve the speed of retrieval and storage, and to pretty much just stay within the realm of the number of staff that are present and the number of staff that are used to handle the system. By scaling, everything can be accommodated for and everything can flow undisrupted. In addition to being scalable, these NAS storage devices also have to have tiered storage. Tiered storage pretty much just allows for input and output of operations that allow for data to be added and accessed with ease and quickly. Fast retrieval speeds are key, and tiered storage satisfies this by allowing for data to be organized based off of necessity. Data that is needed immediately is stored and readily available. Data that is not immediately needed is archived at the lowest possible cost. A good tiered storage system will support a life cycle that provides a home for data flows in each stage of the life cycle, from creation through archiving. This is pretty much achieved by using flash storage, which is the fastest and most expensive, such as a solid-state disk, a spinning disk, which is inexpensive but slower than flash, with speeds of high, medium, and low, and then tape devices, which are the cheapest and most storable, long-term, but much slower to access. It's important to remember that even though that this information is being tiered and stored on different levels, that accessing speed must still be preserved. Now, storage can't just be tiered. Somehow, the storage system also has to be able to manage its own tiering. In order to avoid application or user concurrency conflict, storage needs to be self-managing and be able to handle the tiering of data itself. This is achieved through APIs. Pretty much, applications will tell the storage system what to do, when to do it. There will also be policies that are put in place which make clear how long data should be kept in faster storage before it is moved to slower storage, Tier 1 to possibly Tier 3, and when time limits or size limits should be triggering this migration. If data is staying too long in a higher tier, perhaps it should be archived to move to a lower tier. If the data is too big, maybe it should be archived to save space. Pretty much the system has to be able to determine when this should be done, and it should be able to just manage itself. Another component of big data storage is ensuring that content is highly available. This permits for petabyte-sized information to be stored forever, while also making it highly available. This means that any information that is archived without limiting the availability of that data, or sacrificing processing speeds. By doing this, by ensuring that content is highly available, one would be embracing a business advantage. Now, how does one ensure that content is available? Well, this is achieved by using wide area storage, or what's also known as object storage. In this framework, data is represented as objects, and those objects are dispersed across multiple storage nodes, locally or globally, using algorithms. The object data remains available through other nodes because it's saved there. It's saved there as an object in the memory. By making this data available, one is also making the data accessible and ensuring that the content is accessible. And this means that ensuring it's accessible by any individual in any part of the nation or the world. Global access. Big data storage devices also have to be able to support both analytical and content applications. There's usually massive parallel analysis of big unstructured files that are being done both by computers in computational studies, as well as by human users in a content management application software. Storage needs to accommodate for this dualistic and simultaneous analysis. This will allow for delivery of a single or a set of files to a single user, while data is also simultaneously delivered with integrity to computational analytical environments, such as Hadoop. This will allow for maximum analytical product, maximum analytical results. It will also allow for both computers and humans to work effortlessly without being interrupted by one or the other. Storage devices also need to support workflow automation. Big data has to be delivered to users in workflows. This allows for the transfer information from application to application and user to user. Without workflows, this isn't really made possible, and if it is, it's diminished quality of performance. Integration of workflows is key within these storage devices, for as I said before, that transfer information from application to application and user to user is essential. This is how big data is used and analyzed and pretty much just managed. By using workflow automation, services can be automated, and users and computers are presented with information in a fashion that's clear and cohesive. Storage devices also have to be able to integrate with legacy applications and pretty much just immerse itself and fit perfectly within other devices and structures that exist. There is a need to leverage the latest big data technology. However, this leveraging also oftentimes leaves behind older devices that may not support the new systems or technologies that are being embraced. Systems should be heterogeneous and flexible in order to incorporate existing systems and people. This is essential to big data, essential to the use of data by both individuals and computers, as well as the platforms having the ability for data to be used and analyzed no matter what system they're using. Another key feature of big data storage and access that these storage devices need to keep up with is the integration of public, private, and hybrid cloud ecosystems. There's a movement with big data from transitioning from computer memory and banks of flash drives and wide area storage to cloud computing. Systems are being created from the ground up to be able to adapt to cloud computing, whether in the public, private, or hybrid cloud environment. And this is really good for big data, because vendors and visionaries are creating these network storage devices that are able to automatically implement and adapt to the cloud environment. This means that these systems are pretty much keeping up with the innovation of technology, big data new releases, and things of that nature. By doing this, it can ensure that big data stays ahead of the trend, as well as that businesses are being able to use all of the resources available to handle, manage, retrieve, and access their information. Another feature that storage devices should have is the ability to handle failure, to be self-healing. If there's an outage in any storage device, there should be no evidence of it. There should be an immediate redirection of resources from one server to another. The server that fails should be taken offline for later removal. And this pretty much just allows for the network to continue to work seamlessly and effortlessly. Within a clustered NAS system, within a cloud computing system, or within a wide area storage network, this is pretty much possible because everyone is connected within a cluster, and each node of that cluster shares the same information and capacity to store and retrieve information at every other one. If one goes down, it's fine. This is a distributed file system, which means that every individual and every person connected stays connected because of the fact that information is not stored on one single unit and resources and functions are not capable on just one unit, but on all of them. And so, just to recap, storage devices dealing with big data should be scalable, should provide tiered storage, should be self-managing, should ensure content is highly available, should ensure that content is widely accessible, ensure that there's support for both analytical and content applications, should be able to support workflow automation, should integrate with legacy applications, should enable integration with public, private, and hybrid cloud ecosystems, and they should be self-healing. By doing so, these storage device systems will be able to effectively and efficiently handle big data and satisfy a lot of business needs and business processes that